PSAT, and we were like waiting for like 2 extra hours.
That's funny.
And so we're
Oh, you were taking, I thought you said one time I was taking it. Anyway. Wait, was this in Omaha or?
here. Comes in, and then everyone's like, so this is hot.
Yeah.
And we're just like, not, we're gonna like some Italian afternoon. And then the park's like, why are you like, you got like a male.
Yeah, I mean,
Look at me turning out. I can look down like.
Oh, yes.
I got to do like
Animatronic.
yeah.
Yeah.
Chuck, you're. I can't like look down diagonally. I did the curve. And then like.
Every.
Okay, you can turn to page 41. You like that kind of thing, you think you like, don't give this. Whatever happens, I don't even care. I'm not stupid. Smoking weed. Definitely going to go. It's a sign. Yeah, I know. It's out of commission. And next. Okay, so page 41. We've talked about error bound for alternating series, and we talked about how for alternating series we can get a quick representation of how accurate or worst case scenario of the accuracy of our partial sum simply by looking at the first unused term. And that's a quick way for us to find, it's not the exact error, or it's not the exact value that we're off by, but it gives us a nice quick idea as to how accurate our polynomial is. But that's only for alternating series that converges. What if we had a series that, or polynomial that was not an alternating series, that did not have alternators? We can still find errors, or we can still have an idea as to how off we are from the actual value. We're still going to be involving the first unused term, but it's going to just be a little bit more involved. But it's a similar idea. Okay, so error bound, if you write this down here, error bound is a safe maximum estimation or error for how far off our approximation is from the actual value. So let's say f of x is the exact value, okay, the exact function, and we're using a polynomial to approximate that. And I say p sub n of x because this is going to be just some polynomial of some degree, right? Obviously, the higher, the more terms we have, the better our approximation. But we know that whatever our approximate value is, there's going to be some remainder, and that remainder will help bridge the gap between what our polynomial is versus what our actual value is. So in theory, this is what this is equivalent, right? Now we're not going to be able to find the exact remainder. We're going to just find a safe estimation of this remainder. Okay. So if we have a Taylor polynomial, and it's a Taylor polynomial versus Taylor series because Taylor polynomial has a finite number of terms. So if you have a finite number of terms, we know that at best it's just a really good approximation, but it's still off by some value. So then if I want to find the remainder technically is just the function minus the polynomial, right? It's the gap between the actual and the approximation. So the error or the error bound, the remainder is technically the difference between the actual value, the actual function, and the polynomial version. Give you guys a minute to copy that down. So let's look at this next example here. This is a Taylor polynomial here, f of c plus f prime of c times x minus c. So let's say we're able to work up to some degree, and we want to figure out, how accurate is my nth degree polynomial. Okay, and that nth degree can be 5th degree, could be 8th degree, could be 20th degree. How accurate is this? We want to find a safe upper bound of the accuracy of this partial sum. And we're still going to involve the first unused term to find the remainder. So this is our process here. We're going to find the n plus first derivative, evaluate at c, times x minus c to the n plus 1 over n plus 1 factorial. So we're basically involving the first unused term. If we're trying to approximate the 20th degree polynomial, we're going to use the 21st derivative or 21st derivative value. If we're trying to evaluate the approximation of our 40th degree polynomial, then we'll use the 41st n plus first derivative. But the issue is that the actual remainder is going to be the n plus first derivative evaluated as some unknown z. Right? We don't know what z is, because if we did, then there wouldn't be a need for error bound. We would just be able to find the exact error. But it's an error bound because we know that there's going to be a range of values. So we're just trying to find a safe upper bound of our actual remainder. So all we're going to do is we're going to figure out, okay, at the n plus first derivative, what is the maximum that this can be? And if we can find the maximum that this can be, we can create a safe upper bound. If we can create a safe upper bound, that's all we need. Okay, so our goal is not to figure out the exact, how far off exactly our polynomial is. We just want to find a nice, safe approximation value. Okay, it's like, okay, at worst, we're off by no more than this. Okay, so we're trying to figure out worst case scenario, but the worst case scenario that is still relatively accurate. Okay, if you guys can copy this down here, this is Lagrange error bound, and then I'm gonna go to the next page in a second and kind of break everything down and talk about every little piece that is within this formula, because right now it seems like a lot. So just copy this down, and we'll talk about a more detailed definition or a more detailed breakdown of the next page. And after that, we'll come back and look at some of these examples. So if I want to find my remainder, my nth term remainder is going to be less than or equal to the maximum that the n plus first derivative is. And then the rest is just using the n plus first term So if we're at the 20th term, then this will be 21st factorial x minus c to the 21st power. So we're involving the first unused term of our polynomial. Okay, next page, page 42. And this is where I can kind of break down all the different parts of this Lagrange error bound. So R sub n of x is the error bound or the approximation between the Taylor polynomial and the actual function. X is the given value, and the problem will have to tell you what the x is. C is the center of the function. If it's a Maclaurin series, then you know your center is going to be at 0. If it's a Taylor series, it'll be like x minus 2 or x minus 5 or x minus 7. And those values would be the center of your function. All right. So you should be able to tell by the way the function is set up where the center is. N is the degree of the polynomial. Z is some unknown x value between c and x, where the maximum y value of the n plus first function lies. Now, when applying Taylor's formula or Lagrange error, we will not be expected to find the exact value of z, and also, that's not our purpose, right? We don't really care to find that value of z. Rather, we're merely interested in finding a safe upper bound, a maximum value for the n plus first derivative between x and c, from which we can tell how large the remainder is. So we want to maximize the n plus first derivative on the interval from x to c or c to x. The maximum error is the worst case scenario for the interval in which our actual approximation can live. Right, one more thing down for us. Okay, so I'm going to have one more thing for us to write down. The maximum value at the n plus first derivative will be at x equals c or at our x value. So we only have to worry about testing the endpoints between x and c into the n plus first derivative to figure out the maximum. Okay. Sometimes we can kind of tell we're going to see some problems where it's going to be kind of, okay, it's obvious what the maximum is. Other times, if you're not so sure, you only have to worry about x or c to maximize that value. Some students have asked in the past, well, what if the maximum value was somewhere between c and x? What if, the maximum n plus first derivative was between c and x? How would we know? And the AP exam, College Board, they've ensured that that between x and c, you're only going to get an increasing or decreasing value. So it's not going to be some, because of our limited resources that we have, and a lot of times this is without a calculator, they're going to ensure that the max value is between x or c, or they have to give you something visually where you can obviously tell where the max is. So you're never going to have to worry about anything beyond the endpoints. You just have to worry about, okay, if I want to find this maximum value, just plug in the endpoints and see which one is larger. Whichever is larger will represent that safe upper bound. Okay, let's go to back to page 41. Okay, so the fourth degree Maclaurin polynomial for cosine of x is given by p sub 4 of x. So this is a fourth degree polynomial because the highest degree here is 4. If this polynomial is used to approximate cosine of 0.2, what is the Lagrange error bound? So let's identify all the pieces that we need to plug in. Right. So first, what's our C value? What's our center? 0 because why? It's a Maclaurin, okay. Our n value is our degree. What degree are we working on here? 4, okay. What's our x value? Okay, 0.2, okay. And we know that we have, okay, so let's set everything up here. I want to find the fourth, I want to approximate the fourth degree remainder. I know my fourth degree remainder is going to be guaranteed to be less than or equal to the maximum of my n plus first derivative. So which derivative am I working on here? Yeah, 4 plus 1, therefore. Fifth, okay. So the fifth derivative evaluated at z, we know we're trying to find that maximum value over 4 plus 1 factorial. So 5 factorial. X minus c, our x is 0.2, our c is 0. So 0.2 raised to the fifth. Okay, so really the only thing in question, everything has been resolved with numeric values. The only thing is, okay, what's the maximum that cosine can be at the fifth derivative? Okay, that's where we have to get to. So after you do this one time, I think you're going to see, okay, that cosine and sine is going to just kind of go back and forth. But just for right now, let's see if we can get down to the fifth derivative and just think about that function. So if my function starts off as cosine, f prime is just negative sine. F double prime is negative cosine. Third derivative is sine. Fourth derivative is cosine. And the fifth derivative is negative sine. So we're thinking about negative sine here. Now, it doesn't matter if we're dealing with sine or cosine or negative cosine. What's the maximum value that any of these functions will have in terms of y value? 1. Yep, 1 and negative 1, right? So the absolute value of my error is just going to be 1. I mean, I could test between 0 and 0.2, but we know a safe, easy, safe upper bound is 1, right? The maximum that a cosine and sine or negative cosine or negative sine can be is positive 1. So I can just find, I can replace this with 1 because I know that is a safe upper bound. And now I can find the worst case scenario for my remainder. So I can replace this with 1. So 1 over 5 factorial times 0.2 to the fifth. I know that my fourth degree polynomial at 0.2 is at worst going to be off by no more than this compared to the actual cosine function, which is just a really small number, right? And our approximation is really good because, well, first off, we have a fourth degree polynomial that's already pretty high. And also, we're really close to the center. We're really, as a Maclaurin polynomial, and we're only approximating, we're starting approximation at 0.2. So we're really close to our point of tangency. So it's expected that our actual value is at worst going to be off by no more than this. Yes. 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 Yeah. This is fine. Yeah. You can write like this. I just want to show that, you know, this is just really a small number, right? But yeah, these are fine. These are both fine.
You also write it as 1 over 5 factorial.
Yes. Yeah, that's right. Yeah. Any of these options are fine. Just wanted to show, you know, how small this number is. But yeah, these are all fine. Okay, 43. So you know with sine and cosine, you really don't have to test any values because you know that sine and cosine has a nice maximum value of 1 or absolute value of 1. But let me show you a problem where we do need to test to find that maximum value. So let's look at page 43, number 2. All right, use the third degree Taylor polynomial on the interval from 0 to 1 for e to the x centered about x equals 0 to approximate e to the x. What is the error bound of this approximation? So let's list out everything we need. Okay, what degree are we sitting on? Third degree, so n equals 3. C 0 because centered about 0. X, you spot x, e to the first power here. So that 1 is approximating, that's my x value, e to the x, my x value is 1. Okay, let's build out our remainder. We know we're trying to maximize the n plus first derivative. So we're sitting at 3, so we're going to be maximizing the fourth derivative evaluated at z. We know this is the actual value, but we're trying to maximize this over n plus first factorial, so 4 factorial. X minus c to the fourth. My x is 1. My c is 0, so just 1 minus 0. Again, the only thing we really have to resolve is what number can I replace in for that fourth derivative evaluated at z. So here's the nice thing is that my f of x is e to the x. What's my fourth derivative function going to be? Still e to the x, right? So that's nice. You don't have to find each derivative. You know the derivative is just going to stay e to the x. So we want to find the maximum value that this can be between 0 and 1. So we only have to compare 2 values. We're comparing between e to the 0 versus e to the first power. Which one has a higher value? E to the first. This is my max. This will go in for this. We want to find a safe upper bound. And you only have to worry about testing between the x and c value. Don't have to worry about, oh wait, what if it's stuck somewhere between my x and c? Your function at the n plus first derivative will always be increasing or always decreasing. So it's going to be safe for you to just consider these 2 options. Okay, and then we can just put that all in. It's just e over 4 factorial times 1, and this is the worst case scenario of our third degree Taylor polynomial. We're only going to be off by, at worst, 0.11326. Okay, we'll skip number 3. We'll come back to that a little bit later. That's a little bit more involved. If you can go to practice problem number 1, we've already done one similar to this already. So see if you can try practice problem number 1 and set it up and see if you're able to put things together. So this should be similar to the one that we just did with sine and cosine.
We're doing practice problem.
Yeah. Skip number 3. We're going to practice problem number 1. Yeah. Any questions with number one? Okay, any questions? I want to go back and talk about your quiz for tomorrow. So let me just run through these, what to expect for tomorrow again. So again, your quiz tomorrow will look just like this review sheet. Just have to fill in all the formulas and rules, okay? Indicate the first four terms, the general term and interval conversions. The only thing that's different will be number 5, which has working out the problem and identifying your interval conversions, just like your quiz. But just want to run through these again here. Again, make sure that you have number 4, part C adjusted. My e to the x should be negative positivity, not negative 1 to 1. So I want to make sure that you guys all have that corrected. When you write your general term, you don't have to specify your summation, you just have to be able to write your rule. And then for some of the interval conversions here, it may feel like, oh, I have to, it's like, oh, what if I forget whether it's a bracket or parentheses? What you could do is you could build this from scratch. You could go through a ratio test and then find your interval conversions and test the endpoints. You don't have to, but I'm just saying that, you could, but let's say you did remember it was negative 1 and 1, but you didn't remember whether it was bracket or parentheses. You can plug negative 1 or 1 into your rule of sequence and see if it converges, and just use your knowledge of conversions to see whether you're going to keep the bracket or parentheses. Right. And some of that can be, some of these can be, wait, how do I know whether it's a bracket or parentheses? And if you memorized it, but then you wanted to double check, you could test these endpoints in and just confirm, okay, yes, this does converge, so I'm going to keep that 2. Or I'm not going to keep 0. Or I'm not going to keep 1. Okay. And then as a final reminder, when you're going through a ratio test and you're deciding what your interval of convergence is, I just want to point out, what are the different options there. So first is, let's say you go through a ratio test and all your n's go away because the n's cancel out, and you're left with everything in terms of x. Then you can set your remainder expression to be less than 1, and then you can find most of your problems will be in this form where you can find a clean interval of convergence and then test the endpoints, right? But let's say the other two options are this, let's say the ends do not go away, then what would that look like? Let's say it ends up giving us like n times x minus 3/5. This is obviously going to infinity, so if it goes to infinity, you would say your interval of convergence would be 0, or it's only at x equals 3, right? Even if it doesn't converge anywhere else, it will converge at the center. And then your radius would be 0 because it doesn't extend any place past that point. The other option would be, let's say there's a leftover n, but n ended up being in the denominator. Then this would be 0, and 0 is always less than 1. That means it doesn't matter what the x is, this will always converge. If this always converges, your interval of convergence would be all real numbers, and then your radius would be infinity. So 3 options that you can get out of ratio test for these problems. Either all the either all the n's go away, and it's just what you would expect, a full interval testing the endpoints, or the n's left in the numerator, which is infinity. It doesn't converge anywhere except at the center, and there's no radius is 0. Or the n is left in the denominator, which will force you to be 0, which means it converges everywhere, and the radius is infinity. Okay, so your homework, page 37 to 46, this will be due on Thursday. Tonight, I just want you to focus on practicing through and memorizing your rules. Yeah.
Was today our last day?
Yes, today's last day of notes. Yeah. We are after, yeah. I think we'll probably spend another class period just doing some more practice with Lagrange error, but we're done with notes. We are going to move into test review after tomorrow, and after our test, which I'm going to move to next Thursday. So test will be next Thursday. And after that, we'll begin our putting everything together, AP review. So no more new topics. All right, come get your phones. Health session tomorrow, 7:30. If you need me to go over any of this in preparation for tomorrow's quiz.
So, yes, on the test, I asked you if I just found that this is like geometric, and then I determine, and then like, because all of these include 3, and it's the only one that doesn't include 3. I see. Yeah, and so, yeah, I was just gonna.
Why are we taking a like,
Okay, can you do this right now and just show me the work for these, and then I'll give this one.
I mean, yeah.
Like the purest thing already. Guys, either talk to you. Like I'm looking for.
my mom ran into my old friends on that. Yeah, it's really dumb. But my mom just texted me right after my phone this year, and I wanted to do that, and I thought, I'm like, it's so familiar. And it's like, it's
I mean, it's like building off.
the next job.
Well, I mean, system.
Oh, and then parts.
Thanks, that's much. First one.
Yes, yeah, so the quiz will look just like this, and you have to just fill in each of the definitions, fill it out, the terms, fill it out. The only thing that's going to be different is number 5. It'll be similar to this one, so to work through it.
I feel like just yesterday that was February. And I. Middle of February. Valentine's Day.